developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
It's no exaggeration to say that a critical competition is heating up in labs and factories around the world. The race is on to develop diamond semiconductors for advanced technologies, and the outcomes will have immense importance for the foreseeable future. As an example, drones powered by diamond electronics will dominate the skies since they will fly faster, farther, and with heavier payloads. Not only that, drones equipped with quantum diamond magnetic field sensors will be capable of GPS-free navigation and immune to enemy interference. Here at GLCT, our strategy is to be a self-contained primary source of semiconductor diamond. Our foundation is the highest quality substrates, and we are vertically integrating into devices with the support of the AFRL Midwest Hub. The number one challenge in space is that current electronics are limited to operating at low and medium altitude Earth orbits, where they are protected from space radiation. Our proposed radiation-hard diamond electronics will take the Air Force and Space Force beyond current limitations and into the final frontier.
In this Increment 2 stage of the project, the primary task was to test the device sample grown and fabricated in Stage 1 in a radiation environment that mimics space. The testing was done at the Texas A&M Cyclotron Institute using their radiation effect facility. Our testing was done using xenon heavy ions accelerated in the cyclotron to have an energy of 1.935 giga-electron-volts. Here we see the device mounted for testing. The sample is put in line with the xenon beamline. The device we tested had a lower breakdown voltage than expected, of approximately 50 volts in normal lab conditions. In the first test, we set the device to a reverse bias of 20 volts and applied a dose of 2.6 e to the 7 ions per centimeter squared. Here we are looking at the measured current of the device as a function of time. The ions were applied at the 10-second mark. At around the 120-second mark, it appears that an ion struck the device and we see a spike in the current. Note that the current rises to the microamp range. Intriguingly, the current then falls back to its initial value. After the first test, we increase the flux to 1 to the 8 ions per centimeter squared. Under these conditions, we see more current spikes, which makes sense given the higher rate of ion impact. The device does appear to partially recover, but the higher bombardment quickly spikes the current again. The device was tested again under a highest bias condition of 30 volts, and similar trends were seen, with current spikes associated with higher fluxes and ion strikes. Higher leakage currents limited our ability to test at higher voltages, however. The data show the key results from our preliminary study. It is intriguing that we repeatedly see a recovery effect in the devices during ion bombardment. To understand this result will take further study. In summary, we performed the first tests of GLCT diamond diodes using the radiation effect facility at Texas A&M. The results are preliminary, and we will expand on them in the third and fourth stages of the project. We will make more test devices that perform at higher voltages, in the hundreds of volts, and we will compare all diamond devices to heterostructure devices that have N-type gallium oxide contact layers deposited by AFRL. In the fourth stage of the project, we will return to the radiation test device facilities with the further developed samples and work to understand in detail how diamond diodes operate in high radiation environments.
Diamond has high theoretical potential, and it is time to bring the theory to real life. Diamond has excellent electronic figures of merit and the potential to make electronics more efficient, faster, and smaller.
This project will inform and influence the direction of future investment into diamond. Other countries are also thinking about the capabilities of diamond, and it is imperative that we are leading the scientific discovery and advancement of diamond-based technologies.
This project and the network as a whole have given us at AFRL the opportunity to connect with industry and help promote U.S. industrial capacity to grow high-quality diamond for advanced, dual-use applications.
Broadly speaking, this project will strengthen U.S. national security and leadership in next-generation electronics.